everyone, and welcome to my lab. I promise you a good time, an exciting time, especially if you pay attention. And if you notice that I will be doing a lot of experiments, and I will be obeying all the safety rules, including having my goggles on. And of course, I have a fire extinguisher ready to be used, just in case something goes out of control. We're not planning on anything going out of control, and this fire extinguisher will be just here. I'll take it out of your view so that you get to see everything very clearly. You noticed, of course, that the balloon I brought in had in it a gas lighter than air, as do all the other balloons that I have. That balloon had in it the gas hydrogen, and hydrogen combines with oxygen when the mixture is ignited in a very explosive way. What I'd like to do is show you that same chemistry reaction in the dark. So if we can turn the lights down, we can look at this balloon now, and I bring the flame to it, and with the lights on, did you see that ball of fire? What color was it? Yellow, orange, red is what I hear now. Did you hear sound energy being released when the explosion took place? Yes. What I'd like you to do now is look at that same reaction in slow motion. So let's look at this. You won't hear any sound. There's the flame, and there's the balloon about to be there. And there's that ball of fire. And of course, we don't hear any sound as we look at this in slow motion. So we learn about the explosions differently as we look at them with the lights on and with the lights off. Let's see if I go on now to this balloon over here. Now, I notice some of you are covering your ears. It's because you learned that there might be some sound energy released. So let's try this balloon, and what happened? The balloon popped, but there was no fire. The flame went out, so I'll relight this torch here. That balloon had in it a gas lighter than air, and that gas is helium. So helium is a gas that does not burn explosively, or doesn't burn, period. So let's go on now to the other balloons that we have, and we'll see what happens as I put the torch to this balloon. Ready? Some of you are covering your ears again. All right, here we go. Now, that was a different gas. That's a gas also lighter than air. And I will tell you that gas is called methane. That gas combined with oxygen in an explosive way, but the loudness of the explosion was not as great as it was in the case of hydrogen. So let's repeat that last experiment in the dark and look at this balloon now as I bring the torch to it. Ready? Here we go. With the lights back on, you were able to see the light energy that was released from that combustion reaction between methane and oxygen in the dark. Let's look at that in slow motion and see if we can learn more about the size and the color of the flame. You like that? Yes. Well, thank you. Now, we have one more balloon. We can leave it alone, or we can do something with it. What shall I do with it? All right, all right. One of the things we learned today is that when balloons are ignited, there may be a lot of sound energy being released. So I would like everyone to protect your eardrums before I do this last balloon by taking both fingers and putting them in your ears like so and push very hard. Now, I can't do the experiment and do that at the same time, so I have with me some earplugs which I will use. So I would like you to protect your ears by putting both fingers in your ears, and do that right now. If you can hear the sound of my voice, that means you don't have your ears well protected. Now, I can't hear you, but I can see you smiling. That means you heard what I just said. So please protect your ears as we go to the next balloon and do it in the dark. that balloon had in it a mixture of hydrogen and oxygen. And that mixture is very, very explosive. There was more oxygen available to the hydrogen to combine with, and that's why we heard a louder report and we saw a different color flame. Let's look at that last one in slow motion again and see what we can learn about that. There's the torch coming to the balloon. A much faster reaction, and the color of the flame, of course, was different. So chemicals, when they burn, they produce light energy. They also produce sound energy. There's so many different ways to produce sound. For example, I can take a glass rod and tap on glass vessels. That's one way of producing sound. Or I can just knock on the tabletop. A lot of different ways to produce sound. For sound to be produced, we have to have a vibration. In fact, you hear my voice because my vocal cords are vibrating and pushing the air, and a sound wave is reaching your eardrum, and then a signal goes from the eardrum to the brain. That's how we hear. There are many things that vibrate. Here is a piece of rubber that's been stretched and held in place by 3 nails. And if I pluck this, all I'm doing is producing a vibration that causes sound to be generated, and we hear the sound. There's so many other ways to do this. For example, if I take a whistle and I blow into it, there is a sound wave being generated because the column of air is vibrating inside the length of this whistle. In fact, if I take a piece and extend the length of the whistle, you hear the difference? And if I extend it even more, so the longer it is, what happens to the pitch? The pitch goes down, right? So let's do that. So that's one interesting thing that we want to keep in mind. The longer the tube where the air is vibrating, the lower the pitch. For example, I have this tube, which is hollow. If I blow in it, I just blow air. But if I twirl it like this, hear that? There are so many different ways to produce sound. And to help us understand and appreciate that a bit more, I am right now going to call on a group of talented individuals to help us understand what's going on. So here comes Todd, followed by Brian, Mandy, Fred, and Penny. Remember now, to have a sound, we need something that vibrates. And this something can be a stretched piece of rubber, or it can be a stretched piece of plastic. For example, that's what Todd has. And to produce the sound, we can hit it gently, or hit it a little bit harder. And the loudness of the sound depends on how hard we hit it and on how much the plastic film is stretched. So, Todd, give us a drum roll and see. It sounds pretty good, huh? Yeah. Like that? Yeah? So that's one way of producing beautiful vibrations. Let's see if we can listen to other vibrations. Mandy, can you pluck one string on your cello? How about plucking another string? A third one? A fourth one? Now, can you pluck them all very quickly? Faster, as fast as you can. Actually, there is a way in which you can even pluck them much faster than that. That is to use the bow that she's holding. The bow is made of horsehair, and some rosin has been put on the horsehair so that when she pulls the bow across, then she will pluck all 4 strings at the same time very fast. So, Mandy? You like that? Huh? Remember, we can generate sound waves also by moving columns of air. And that's what we have now in the tube that Fred is holding. What's the name of that tube? Clarinet. It's a clarinet. So Fred has a mouthpiece. Inside the mouthpiece, there is what we call a vibrating reed. So Fred, would you please let us enjoy what you can? And can you move up the scale?
Yeah, I can do that by lifting my fingers off of the hole so that I shorten the column of air.
You like that? The second wind instrument we have is the saxophone. So Brian, can you do the same things that Fred just did? That sounds pretty good, doesn't it? The last wind instrument we have is the trumpet. And the trumpet, of course, has a mouthpiece. Penny, can you blow air through the mouthpiece? No sound whatsoever. We need to generate a vibration. So could you attach the mouthpiece to the trumpet and blow again? Same thing. So we must have a vibration. So how do you do it, Penny? But you actually do it with the trumpet close to your mouth, right? Go. Isn't that beautiful? Now, how about hearing something from the Science is Fun Quintet? Are you ready? Bravo! Very nice, very nice. How about an encore? Right. Would you like an encore? All right. Bucky, and welcome to my lab. I'm so happy to see you here again, and I'm sure you and I would like to ask the audience to give our quintet another round of applause.
You can make a xylophone at home. You need 6 glasses or glass bottles that are the same. Pour a different amount of water into each bottle. Tap the sides of the bottles with the metal spoon to hear what sounds they make. You can tune your xylophone by adding or removing water from the bottles. Then, create your own music.
Let's see if we can produce another sound by taking this empty bottle and blowing through it. You hear that? In fact, that's an experiment that you might want to try at home by putting different amounts of liquid in the bottle, because that changes the height of the column of air that's being caused to vibrate as you blow into it. So another way of, let's try this. I take my finger, I wet my finger, and I turn this I have to have a clean finger to do this. Okay, I have a soap solution here to clean my finger, and I'll reach for paper towel and try this. So we're causing a vibration to take place here, right? Maybe I try this one here. No. Patience is what we're after. So what's going on here is that all of these different shapes that we have the glasses in are actually undergoing a vibration, and it looks like this. If I take this plastic cup to show you, this is the vibration that's actually taking place, and if we can achieve what's called resonance with the frequency of that vibration, then we can generate the sound that the different sounds that we heard. Now, there's still more ways to generate sound. You all recognize this instrument. What's this? What does it look like? It is a. Yeah, somebody said it's a baseball bat. No, it's not a baseball bat. It's a pipe organ, and if we blow air through it, we're causing a vibration. We're generating what's called a standing wave inside this tube that causes sound to be heard. Now, it turns out that the velocity of sound, the speed with which sound travels, depends on the kind of gas that you have inside the pipe. And what I'm going to do is move over to this side and ask Julie to come out and help. Julie, would you please come out and help do this? Please welcome Julie. What we're going to do is very gently blow a gas which has a smaller mass, a smaller molecular weight, as we call it, than air. So let's try that. This gas is helium. You hear a difference? So what happened to the pitch? Went up, right. So now let's try a gas that is heavier than air. This gas is called sulfur hexafluoride. So let's blow that. And we have to kind of blow the helium out and the air out too. So go ahead. What happened to the pitch here? Went down, right? So that's something to keep in mind as we listen, and thank you, Julie, as we listen and appreciate different sounds that are produced in a variety of ways. Now, Julie, don't go away, because I need you to help me with this next experiment. This next experiment is one where I have a piece of copper in this shape sitting on top of this tripod, and there's a burner underneath it, and the piece of copper is shiny. So if Julie be kind enough to turn the gas on, then I can light the burner, and what we want to do is heat this piece of copper and try to see if there are any indications that a chemical reaction is taking place. One of the indications that we look for is what? We've already talked about it and seen it before. Color change, right. So that's what we're going to look at. We want to see if there is a color change on the surface of the copper as it's being heated. The copper itself is not very reactive at room temperature, but when it gets heated up, we can see already. Can you see any evidence of a chemical change? We see the change in color. That's because oxygen from the air has combined with the hot copper to produce a layer of copper oxide. So what we're going to do next is to see if we can clean off this layer of copper oxide by turning off the gas and very quickly bathing this copper oxide with hydrogen gas that's coming out of this funnel. So here we go. There's copper oxide. Copper oxide. We do this with, turn the hydrogen off, please. We do this with no flames around because we already know what happens to hydrogen, right? And so this is a way by which we can show how the conditions of the experiment, then the change in temperature in this case, affects the reaction. Thank you very much, Julie. Now I'd like to ask Fred to give me a hand. Here is Fred with the tall glass tube. This glass tube looks wet on the inside. I have a step stool here that I'm going to stand on. This tube looks wet on the inside because it has a liquid in it. It also has a colorless gas. We can't see it because it's colorless. And what I'm going to do is take the rubber stopper that's on the very top, lift it up after I strike a match so I can drop the lit match into that tube, and we're going to do this in the dark. All right? So I'll strike the match, take the top off. This experiment released energy in the form of light. We saw that. In the form of sound, we heard that too, right? And also there's a deposit of this yellow substance on the inside of the tube. That's sulfur. What I'd like to have us do now is to look at this in slow motion and see if we can learn more about this exciting experiment. Again, we won't hear any sound. There's the match being dropped in. There I am trying to get out of the way. All right, let's do another experiment. Actually, let's do this experiment by taking a clear and colorless liquid and mix it with a clear but colored liquid in this very special glass assembly where there is a glass funnel at the top connected to a spiral glass tubing, which then leads to a receiving flask at the bottom. So we'll mix those two liquids together in the dark, and we'll see what happens. So let's turn the lights off. This mixture generated light energy, no sound energy, and I can tell you by touching it, it's still at room temperature, so no heat energy. When we mix chemicals together and we generate only light energy, we have something called a chemiluminescent reaction. So the phenomenon of chemiluminescence is what we have just seen here. Of course, just about everyone knows about chemiluminescence because you know about the firefly reaction. The firefly reaction is bioluminescence. It's taking place in a living organism that has a catalyst that makes that reaction go. I'd like to close this very special presentation by reminding you to enjoy doing experiments, to have fun as you do experiments safely, and to remember, no matter what you do, that science is fun. Thank you very much.
Check out the Science is Fun website.